Yes.
Okay.
The daughter's holding up, that's the family.
Okay,
Go
good, yeah.
many
That's right. She doesn't have any illnesses, right? She doesn't have any illnesses other than Parkinson's,
Yeah,
right? So,
okay, well, that's maybe some slight relief.
yeah, right, I think so, yeah, yeah.
I mean, what do they do with the recording if not put it online?
I kind of
They
look at
share it just
everything in
with
the
the
past.
other faculties that might not look at it.
Yeah.
You know what, let me take a look.
Yeah, there's
at
been a
how
lot
it turns
of
out
students,
first,
faculty,
and then I'll
lately.
I'll describe. Yeah.
Okay.
Oh, okay.
Yeah, that's for the phone.
Right.
Thank you everyone for coming. It's my great pleasure to introduce my friend, my mathematical brother, and yeah, my former office mate, Dor-on, from Haifa University. He's going to talk about symbolic dynamics through the lens of C-term algebra.
Okay, thank you for the introduction for you. And thank you for the organizer or the organizers for inviting me to give a talk in your colloquium. It's always an honor to give a colloquium talk, and you might see that the title is a little different than what was announced. So don't complain, because the talk that I actually wanted to give in this colloquium was recorded by Boyu in his analysis seminar. So if you're still interested in what was showcased in the abstract of the colloquium, you can see the recording. So no harm, no foul, but I felt like this talk would be more accessible, and so I decided to switch the talks. Okay. So, yes, so I'll talk about symbolic dynamics through the lens of C-star or algebras, and yeah, this is joint work with several people that I'll get to mention throughout the talk. But first, I sort of want to outline the talk. What am I going to be discussing? So I'll talk about subshifts of finite type. I'll explain what they are and some of their properties. In subshifts of finite type, they're identified up to a certain notion of isomorphism. Yeah, so in that category, the right notion of isomorphism is the concept of conjugacy. And I'll explain what are known obstruction. I'll talk about some obstructions to this conjugacy of subshifts of finite type. And then I'll sort of, there will be an intermezzo where I will sort of explain philosophy due to von Neumann that explains why studying classical theories in mathematics through the lens of algebras or operator algebras can be very fruitful and very insightful. And then, of course, I'll introduce sort of the type of algebras that I and others associate to subshifts of finite type or to directed graphs, and explain how some certain equivalence relations between subshifts of finite type are captured through these algebras. This would be sort of the main question that I'll address in this talk. And finally, I'll start talking about the methods of proof that we use for the theorem that involve bimodules, C-star bimodules, and in fact, some new techniques from the theory of bicategories. By categories. Okay, so by categories. I mean, we all know, like, when somebody mentions category theory, they tell us, oh, this is abstract nonsense. Technically, this is false, because it really helps us understand mathematical theories in certain contexts and provides insights. It's not something maybe that you can measure mathematically. I think some people can measure it mathematically, but even if you can't, it's something that does indeed provide insight where insight is hard to find. And okay, so if you're skeptical about category theories, then definitely you're going to be skeptical about bi-category theory. You know, that's even more abstract. Diagrams are not needed. They no longer necessarily commute. They commute up to some identification. It's more complicated. There are arrows between arrows. And you would say that's even more abstract. And I want to convince you today that bi-category theory is absolutely necessary. And category theory is not enough. So if you are an algebraic topologist, you would already agree with me, because you know these people already use this kind of machinery, this contraption all the time, and they know its benefit. But I was a skeptic. Okay, I was very skeptical because okay, I could see like why category theory would be useful, but why would bi-category theory? It's absolutely necessary. Absolutely necessary, and this is what I'd like to try to convince you of today. So, subshifts of finite type. So suppose that I have a directed graph, so it has a collection of vertices, a set of vertices, a set of edges, with source and range maps, right? So source and range, given an edge, they give me vertices, which are the sources and the ranges of the edge. And if there are no sources, no sinks of this graph, right? So no vertex that has no incoming edges, and no vertex that has no outgoing edges, then I may construct a so-called topological two-sided edge shift. So what do? I take the product of this finite set of edges, indexed by the integers, and by Tikhonov's theorem, we know that this has a compact, this is a compact topological space with the product topology. And so we can induce on the subspace this topology. This is a subspace of so-called concatenatable edges, otherwise known as bi-infinite paths in this graph, right? So this is a sequence of edges that concatenate well with each other, and so that sort of makes sense to call this the set of bi-infinite paths, and this is how you topologize it. And together with this bilateral shift operation, you get what is called a subshift of finite type, right? So whenever you have an edge, you sort of shift it towards the left, and you get yourself sort of dynamics, right? Things sort of move around. You can consider orbits, maybe, and you can consider long-term behavior of this system. And these are some of the most simple dynamical systems. They're sometimes called topological Markov chains, because whenever you are at a certain point, you only need to know where you are in order to know where you need to go forward, where you're able to go forward. Just like in a Markov chain that doesn't care about the past, only cares about your current position, right? But it's a topological version. There's no like probability involved, and it can model a lot of various topological phenomena in dynamics and ergodic theory. But it has this sort of very combinatorial nature that really helps us capture it and understand it. And despite it having this so-called combinatorial nature, there are still some very fundamental questions about these subshifts of finite type that are still not answered even today. So maybe I should start talking about how to identify various kinds of subshifts of finite type. So suppose I have this graph, which has a single vertex and two edges. So you can see already I allow multiplicity of edges, for instance, in my directed graphs, and definitely I allow loops, right? So, but I can also take this sort of graph, and if you look at this construction, I take a directed graph, and what I can do is I can think of edges of that graph as vertices, and two paths of that graph as edges, where the range of a two path is the second edge, and the source of the two path is the first edge in that two path, right? That's called the line graph construction. Sort of very standard kind of construction in combinatorics. And this is what you get when you apply the line graph construction to this graph. You get this one. Okay. And yeah, so the point is that if you take the rule which sends a 2-edge to the second edge, that actually extends to a homeomorphism of the associated subshapes of finite type for these graphs. And it extends to a homeomorphism that actually respects the shifting operation. Okay, so if you shift and then apply the homeomorphism, it's the same as applying the homeomorphism and then shifting. This is the concept of conjugacy. Okay. Suppose you have two such subshifts of finite type for two different graphs, like so. They're said to be conjugate if there's a homeomorphism that respects the shift. Okay, and as you can see, the graphs can be quite different from each other. Don't have to have the same number of vertices, edges. They could be quite different, but still, the systems, the dynamical systems, would be the same. And I would say that these two subshifts of finite type are eventually conjugate if there is some iteration number, starting from which there's a homeomorphism between the iterates, the respective iterates of the dynamics. Yes? However, I want to warn you that the homeomorphisms that implement the conjugacy between iterations, they don't have to be the same. Right? So for instance, if I have two iterates which are co-prime to each other, and they are conjugate via the same homeomorphism, then the original systems are conjugate to begin with. That's an exercise that you can think of. Why is that true? Okay, so most of the time, if these notions were to be different to begin with, which is not clear at the moment, yes, then you would not expect the homeomorphisms implementing conjugacy between iterations to be the same. Yeah. Okay, so matrix formulation. So you come up with a notion of conjugacy, and this is kind of a classical question in whenever you consider a class of dynamical systems. When are two dynamics in a class conjugate to each other? When are they the same dynamics? Can you find an algorithm which terminates given two such dynamics, determining whether they are conjugate or not? That's the question of decidability for conjugacy. Let's say for us in the class of subshifts of finite type. Okay. So this question was considered by Williams in '73, and he came up with matrix formulations that encode these two different notions of conjugacy that I presented to you. Suppose I have two essential matrices, so you should think of them as adjacency matrices of the corresponding graphs. Yes? So essential means that they have no zero rows and no zero columns, which corresponds to the graphs having no sinks and no sources. Okay? So that's what I mean by essential. It's just adjacency matrices of the graphs that we've considered so far anyway. And they're indexed by finite sets V and W, and we say that they are a shift equivalent, and we denote this by A tilde B. If there's some lag, some number of steps, I like to call it, such that A to the M is equal to RS, B to the M is equal to SR, R intertwines A to B, and S intertwines B to A. Okay. That's some relations, you should think, some relations between adjacency matrices. R and S don't have to be squared, mind you. Okay. But they still have to have like non-negative integer entries. Okay. So that's one notion. Another notion is that of so-called strong shift equivalence. And strong shift equivalence tells us, and that I'll denote by A cong B, if there are of like M, if there are M R matrices, not necessarily squared, and M S matrices, not necessarily squared, such that A is the multiplication in one way, and then the multiplication the other way is the multiplication of the one way with the R2 and S2, and then you sort of switch the order of multiplication between these things, and that's allowed. Eventually, if you do this M steps, you get from A to B. Okay? And it's easy to see that strong shift equivalence implies shift equivalence. Why? Because you can just take the product of the R's and the product of the S's, that would be your R and that would be your S, and that would give you shift equivalence. Okay. So what's so magnificent about these relations between adjacency matrices? It's the fact that you can capture conjugacy and eventual conjugacy in terms of these equivalence relations on adjacency matrices. So I will denote by XA sigma A the subshifts associated to the graphs of A and the shift of the graph of A. And the theorems of Williams and Kim and Roush from 73 and 79 say conjugacy is the same as strong shift equivalence, and eventual conjugacy is the same as shift equivalence. Okay, so you want to ask the question of decidability. Now the questions become simpler, right? Because these are like matrix problems. This is a problem in matrix theory, which is like potentially more tractable, right? That was a nice paper. But let's consider the following example. These are a couple, so these are sequences of pairs of 2x2 matrices, AK and BK. And it is known that for any K, AK is shift equivalent to BK. But for K greater than or equal to 4, it's not even known if they're strong shift equivalent. This is like a travesty. These are such simple examples, right? 2x2 matrices, one with entries 3 and 4, the other with matrix 12, entry 12. And we still can't say, for this A4 and B4, we still can't say if they're strong shift equivalent. That's embarrassing. I am embarrassed. Okay? So anything we can say, anything about strong shift equivalence, while merely assuming shift equivalence, is already magnificent. It will already be great, like groundbreaking, as far as I'm concerned. Okay? Because even in these simple cases, we don't know. Okay, I should mention that for the K equals 3 case, Baker used a computer search that showed that they are, okay, so they're, first of all, they're shift equivalent of like 3, A3 and B3, are shift equivalent of like 3, and they're strong shift equivalent with like 7. So you have to go through 7 steps. You have to increase the matrices like to 4x4, even 5x5 along the process to get from A3 to B3. That's crazy. And he came up with this, like using a computer search. Okay. I think that's interesting. So yeah, here's Williams' problem from 74. He, in his paper, claimed that shift equivalence and strong shift equivalence are the same. Okay, but I just told you that I don't know if these A4 and B4 are strong shift equivalent. So what goes wrong? Okay, so let's see. First of all, Kim and Roush were able to prove in 79 that shift equivalence is indeed a decidable equivalence relation. That means that there's an algorithm which terminates, given two such systems, telling you whether or not they're shift equivalent or eventually conjugate. Yeah, there's an algorithm for that. However, 20 years, this problem of Williams was open. There was a mistake in the paper. And Iratum followed a year later. And but eventually it was shown to be false. This is a counterexample appeared in the Annals of Math. The second one, irreducible, showing that there are 7x7 matrices A and B, which are shift equivalent, but not strong shift equivalent. Crazy. Absolutely crazy. And the point is that even in their paper, Kim and Roush admit that it was very, okay, they come up with this invariant, it's called the sign gyration invariant. And they admit in their paper that it was very difficult to compute it and to find these matrices. They had to satisfy like a bunch of properties. It wasn't even clear that such matrices exist. They ran a computer search as well, and they were able to find it after many iterations. So it was very, very difficult for them to find it. And so the issue is that the invariant that they produce is very difficult to compute. Okay? And so what has become known today as Williams' problem is coming up with something that is more computable, right? Being able to produce more counterexamples that we would maybe be able to understand the obstruction, right? Whenever you come up with a counterexample, what's the next thing you do? You try to measure an obstruction. And then when that obstruction vanishes, then you know that you still have a theorem, at the least, right? At the very least. So that's kind of a natural thing that we do in mathematics, Okay, especially in algebraic topology. It's very, like with homological invariants, this is what we do somehow, yeah? Or one of the things that we do, I should say. So I would like to present a new approach to measuring the obstruction to strong shift equivalence while merely assuming shift equivalence. Suppose I have a U times V matrix R over the natural numbers. I can define what would be the analog of the graph over that matrix. So ER is the collection of triples, yeah, with fixed source and fixed range, and I iterate them according to their multiplicity appearing in the matrix R. So this is what I do here, yeah? I look at the entry here, which tells me the multiplicity, and I multiply here the number of times such a triple appears, right, for a fixed U and V. So that gives me a directed, well, an analog of a directed graph. It's not exactly a directed graph, because now the source map and the range map, they don't go to the same set anymore, right? But it's still defined. And if R was square over V, meaning that U was equal to V, then I would get the construction of the directed graph associated to that adjacency matrix. Right? So these are sometimes called graph correspondences. Okay. Because they correspond one graph to another, maybe. Not so clear. Okay. And just like you can multiply adjacency matrices, you can sort of multiply these graph correspondences if the sets sort of coincide for them. So if I have another such adjacency, or maybe not an adjacency matrix, but some matrix, rectangular matrix, over V and W, I may form the so-called fibered product, where I take pairs like so when they're concatenatable. Yes? And this actually turns out to be naturally identifiable with the edge set. I call these sometimes edge sets, the edge set of the matrix R times S. Okay? So now we're sort of starting to think about these things functorially, right? We have this adjacency matrices are mapped to directed graphs. So now maybe some kind of morphism between adjacency matrices. This R would be mapped to a morphism between directed graphs, but it's not exactly a graph homomorphism the way that we know. And of course, here in this situation, if R is equal to S is both squared, then taking this fibered product just gives you the set of two paths of R when it is an actual adjacency matrix. Yeah? And if you repeat this n times, you get the set of n paths. Right? So this is some way of looking at paths that are interacting with different matrices, coming from interactions of different matrices. Okay. And okay, so where do path isomorphism actually, or graph isomorphism really come into play? They come into play when you try to identify morphisms. So this should already hint at morphisms between morphisms, right? Or natural transformations in the theory of categories. So this is where this comes in, the so-called a bijection like so would be called a path isomorphism, or an isomorphism of graph correspondences, if it merely preserves the range and source. And of course, this is what you're used to maybe in graph theory, directed graph theory. Two graphs directed are isomorphic if there's a bijection between the edge sets that preserves the range and source. Right? So this is a generalization of that concept. Okay? Okay, so while looking for another way of measuring the obstruction to strong shift equivalence from shift equivalence, we sort of stumbled upon the following equivalence relation. So suppose I have two essential matrices indexed by V and W, they're both square, A and B. We will say that they are aligned shift equivalent with lag M. If there are rectangular matrices R and S, with entries in the natural numbers, together with path isomorphisms satisfying certain relations. So what are the path isomorphisms? So here's one. If you multiply, you take the fibered product of R and S, you get A to the N. That should appear familiar from the concept of shift equivalence. This is another such relation. S times R is equal to B to the N. But now I'm not multiplying matrices anymore, mind you. I'm identifying sets. Okay, and of course, whenever I multiply matrices, I can come up with some kind of bijection like so. If I know that R times S is equal to A to the N, I can definitely produce such a bijection. And the same with S times R is equal to B to the N. I can produce such a bijection. So the existence of these bijections is merely equivalent to shift equivalence. It's the same as shift equivalence up to now. What makes this aligned, what makes this more interesting, is that they have to satisfy these extra relations. Now, don't be alarmed. I still don't understand these relations to this day. Okay, these relations are very mysterious. Okay, I mean, we do understand them a little better now, I have to say. So when I first looked at this, I talked to my algebraist in my department and I asked them, you know, there has to be some categorical interpretation of what's happening here. And they couldn't tell me. Like people working in category theory, I guess not in bi-category theory, but in category theory, they couldn't tell me what was happening. So bear in mind, you know, we have these relations, we don't understand what they mean. I didn't understand what they mean. I guess my pitch is that we now have a way of understanding what they mean. Okay? So yeah, we looked at them and we didn't know what to do. So in a research exposure week at the Technion in September 22nd, I asked a bunch of an undergraduate student. There were two initially, but then there was only one. I asked, is this notion even an equivalence relation? I mean, I define it to be like, I use the word equivalent here, but it's not even clear if it's an equivalence relation at this point. Okay. I also asked, does this aligned shift equivalence imply strong shift equivalence? And can I take A3 and B3 in this example that I showed you and use aligned shift equivalence to tell them apart? Okay. So three nice questions, you know, that we can write a computer program, we can do some math, and yeah, so indeed with Eilers and Idan Pazi. Eilers is a professor at University of Copenhagen, where I did my postdoc, one of my postdocs. Idan Pazi was the undergraduate student that I supervised during that week. And we wrote a computer program that did item 3 with lag 3. So aligned shift, they are aligned shift equivalent with lag 3, with 3 steps, which is better than 7. Okay. So combined with the following result, it gives a new way of distinguishing A3 from B3 in a faster way. Algorithmically, it runs faster. Because it's only 3 steps, yes? So with Carlson and Niles, we proved a part of this, and with Bilic, my PhD student, and Luis from University of Hawaii at Hilo, we proved the following. Then strong shift equivalence is the same as aligned shift equivalence. In particular, aligned shift equivalence is an equivalence relation. Okay. All right, so we answered all 3 of these questions. But yeah, and this is already sort of interesting because it makes for an obstruction, right? So what is now the obstruction to strong shift equivalence? Well, merely assuming shift equivalence. It's the validity of these relations. That's what it is, yeah? That's what it's become. So we really need to understand these relations. That's the crux now. That has become the crux. Okay, so how did we come up with this aligned shift equivalence? Turns out it arises from attempts to encapsulate strong shift equivalence and shift equivalence through the lens of algebras. C-star algebras, operator algebras that sort of arise naturally from these subshifts of finite type. So I'd like to define to you these algebras. But before I do that, an intermezzo, as I promised. So yeah, this idea of associating algebras to classical objects has been extremely fruitful, especially in combinatorics when you sort of try to do some counting problems. For polytopes, this is extremely useful. There are these all sorts of kinds of algebras that are very useful in counting problems. But also here, von Neumann algebras were used to come up with new invariants for topological groups in analytic group theory. There's this sort of famous result in dynamics due to Giordano, Putnam, and Scal. So suppose you have, okay, I'm going to change a little bit the class of dynamical systems that I'm considering now. Suppose you have a minimal homeomorphism of Cantor set. What is minimal? It means that there are no proper non-trivial closed subspaces that are invariant under the homeomorphism. That's a minimal homeomorphism, okay? And they wanted to classify minimal homomorphisms on counter set via something called orbit equivalence. And orbit equivalence means that the homomorphism maps an orbit to an orbit. Okay, if you know what that means. You just take a point and you look at all iterations of that point, that's an orbit. Back and forth, right? And it was open for a long time. And it turns out that using C-star algebras, you can come up with an invariant that completely classifies Cantor minimal systems up to orbit equivalence. Of course, now it's been stripped of the operator algebra arguments. It can be done completely dynamically. But I argue that one of the key ingredients of the proof is still equivalent to something that comes from K theory of C-star algebras. And whatever you do, you can't get rid of that thing in the proof. So it's an equivalent formulation. It's a definition that comes from studying C-star algebras that people have not thought about until the point where these Cantor minimal systems were considered through the lens of C-star algebra. So I want to do the same thing. This is for Neumann's philosophy. Encode something that's very difficult, like the decidability, let's say, of subshifts of finite type, or this problem of classifying Cantor minimal systems through up to orbit equivalence. Try to encode that through the lens of C-star algebras or pure algebras potentially, and maybe you can come up with new ways of measuring invariants like we saw, and potentially even answering some open problems. Yeah, so this problem of classifying Cantor minimal systems up to orbit equivalence was an open problem for a long time. So yeah, so this is how I'm going to do it. Suppose I have a directed graph, finite, no sinks, no sources. I'm going to define an algebra. It's a complex algebra. It's called the Levy path algebra, and it's the universal star algebra, meaning there's some kind of involution on it, generated by elements, vertices, edges, and edges that go back. These are the stars. Okay? And it's the universal algebra that is subject to certain relations between the generators, right? We all know how to take the free algebra generated by a bunch of generators. Now impose some relations. That means you take a quotient of that algebra by the relations, yeah? Just like you may do in group theory, for instance, yeah? Every finally generated group is a quotient of the free group, right? On n generators, because you just impose the relations that, right? So this is an analog of that in the algebra world, yeah? What do we require of vertices? If you multiply two vertices, they are zero unless they are the same vertex, meaning that's an idempotent. If you multiply sources of an edge and ranges of an edge appropriately, you don't change that edge. And the same for the edge going backwards. And if you multiply an edge going backwards with an edge going forward, then you get the range of that edge if the edges are the same and zero otherwise. And there's some asymmetry happening. If you just sum up overall edges going forward and then backward that are emanating from the same vertex, you get back the vertex. Okay. So these are sometimes called the 4 and 5 are sometimes called the Kunz-Krieger relations. Because Kunz and Krieger worked on these the non-completion of these algebras. So the graph C-star algebra is some kind of non-completion of this Levitt path algebra. Here's one way to do it. Take all star representations of the Levitt path algebra into bounded operators on Hilbert space, and then take the supremum norm over all such for every element. Turns out that's a norm. A priori it's only a semi-norm, but it turns out that that's a norm. It's injective. It doesn't annihilate anything in this complex Levitt path algebra. And that's some kind of norm completion. It gives you a Banach algebra, a Banach star algebra. It has an involution on it. And in fact, it is a C-star algebra in the sense that it is a sub-algebra, norm closed, adjoint closed of bounded operators on Hilbert space. Okay. Now, what is important here is to distinguish the algebraic between the analytic. In algebra, in pure algebra, we can take like a polynomial and apply it to an element, and we get another element. This we can of course do in C-star algebras as well. But the advantage of living in this category of C-star algebras is that if you have a normal operator, so an operator that commutes with its adjoint, yes, you can actually apply a continuous function that's defined on the spectrum of that operator. This is something you normally cannot do in a pure algebra because you would exit it.
What's this S and R?
S and R are the sources and range maps of the directed graph, yes? So this is a vertex, S of E is a vertex.
Oh, it's a map.
It's a map, that's right.
Oh.
S and R are maps from E to V.
Okay.
Yes, that tell you what are the sources and ranges of an
Go
edge.
back.
Yes,
Okay.
okay. So far, so good?
Mhm.
So there's an advantage to using C-star algebras as opposed to regular algebras because they are more flexible in that sense at least, that you can apply continuous functions and not just polynomials or star polynomials to elements of that C-star algebra, yeah? And still remain inside the C-star algebra, that's the point, yeah? Of course, you can do it to an element in the Levitt path algebra, but you may exit it. You may become outside of the Levitt path algebra, yeah? As soon as you do that. Okay, so this is the algebras. I want to now discuss additional structure associated to these algebras that allows me to capture shift equivalence and strong shift equivalence. This is what I'm headed towards. So for a path in G, we denote by absolute mu the length of that path. And because of relation 4, every star monomial in generators can be written as a path times an adjoint of a path. Let's think about that for a moment. Look at relation 4. What is a star monomial? It's a bunch of multiplication of elements and their adjoints. Yes? Because of item 4 here, whenever there's an adjoint to the left and something without an adjoint to the right, item 4 over here tells me that I can cancel it or I can move it forward. And if I do this a bunch of times, I will see that every star monomial has this form. Okay? So for some paths. Okay, so we get a Z grading of the Levitt path algebra. Z grading, it just means a collection of subspaces that are linearly independent, indexed by the integers, such that if you multiply one and the other, you land in the appropriate one. That's a Z grading. And here it is. It's the span, linear span, no closure. This is Levitt path algebras, pure algebras of nu star, where the difference of lengths is fixed. That's the nth graded component here. Turns out that yields a Z grading. And if you close up these spaces, you get a Z grading of the C star as well. Right? Close it with respect to the norm. Oh yeah, I should probably say that the choice here of completion doesn't actually matter. If you take any norm, which is satisfies certain C star relations, and you close up with respect to that norm, you get the same C star. Okay, so it's not important that it's this specific norm. Almost any way that you complete it would give you the same thing. Okay, I should say that. Okay, and we also have a distinguished commutative subalgebra. It's the span of mu star. So the same path for forward and backward, mu star. Turns out this linear span is an algebra. Okay, and yeah. That gives you a commutative subalgebra, and you can close it up. That would be then in the C star algebra. And it turns out that you can already see a hint of the dynamics in there.
Mhm.
Because of
the graph is finite.
the graph, everything is finite.
Oh,
yes.
okay, so that's a finite dimension.
Yes. And no, this is actually not a finite dimensional algebra. Because paths can have arbitrary length.
Oh, upper length, okay.
Yes. But that's a good question. Yes. But my graph and edges and vertices are all finite. Yeah. So already here, if you close up this so-called diagonal commutative subalgebra, you get a hint of the dynamics. What is this? It's continuous functions on the one-sided shift. So remember how we talked about the bilateral shift? There's a unilateral version of that, where you just take one-sided infinite path and you shift towards the left and delete the first edge. Yes? So that's also a compact Hausdorff space. Just like the bilateral shift, edge shift. And already here you see this diagonal subalgebra gives you this unilateral edge shift. Okay, that's interesting. So I would like to denote by boldface K the closure of finite rank operators on little L2 of the natural numbers. So little L2 of the natural numbers is a Hilbert space, sort of the canonical example. Yeah. And if I close up in the operator norm, I close up the finite rank operators, I get what is called the compact operators. And I would like to denote by C0 the closure of diagonal compact operators. The closure of diagonal finite rank operators. So what are diagonal operators? Okay, little L2 of n has a standard orthonormal basis, right? These vectors that are 1 at a single entry and 0 for the rest of the sequence, right? A diagonal operator sends such a vector to a scalar multiple of itself. That's a diagonal operator on that space for me, okay? So I can take the closure of finite rank diagonal operators, that's called compact diagonal operators. And here's a theorem. I already mentioned Kunz and Krieger, they worked on this in 1980. So suppose I have two finite essential matrices, and then Carlson and Rout, they sort of prove the converse. So the following are equivalent. The matrices are strong shift equivalent if and only if the Levitt path algebras are so-called graded Morita equivalent in a way that respects the diagonals. And equivalently, the graph C-star algebras up to tensoring with compact operators here are graded star isomorphic in a way that preserves the diagonal, but now tensored with diagonal compact operators. Okay, so diagonal tensor diagonal, so that it would make sense. Okay, so what is a graded Morita equivalent? Maybe I should say. So if I have two rings, R and S, they are said to be Morita equivalent if there are bimodules between them, let's say M and N, such that N tensor N over S is isomorphic to R, and N tensor R over R, N, M is isomorphic to S. Okay, that's just Morita equivalence, okay? But graded Morita equivalence means that if you restrict your coefficients there of the bimodules to be in the graded components or in the diagonal subalgebra, you land in the appropriate place. Okay, so you can make sense of what that means to be a graded Morita equivalent. Okay, fine. Okay, so we can capture the more difficult of the two relations, strong shift equivalence. The situation for shift equivalence is a lot more nuanced, a lot more difficult. It's the decidable relation among the two that we know at least is decidable, but operationally, it's much more difficult to work with for some reason. So here's a conjecture of Hazarat from 2013. The matrices are shift equivalent if and only if the Levitt path algebras are merely graded Morita equivalent, not necessarily preserving the diagonal anymore. Okay? The C-star analog of this would be that the graph C-star algebras are graded star isomorphic, period. Don't have to preserve the diagonal subalgebras anymore. Okay? So here's some partial results or results that are known for at least graph C-star algebras. So there's this very vast area in operator algebras, this field of operator algebras is called classification of C-star algebras. So they use K groups to classify C-star algebras up to star isomorphism. Okay, this is so-called the Elliott classification program. But it's only for simple C-star algebras. Our algebras are not simple. And we have to do classification up to additional structure. We want to preserve this grading. We want to preserve the diagonal maybe. So, but still, through K theory, there's this one-way direction, one directional result. So this was proven by Krieger in the 80s, and then for Levitt path algebras by Hazarat in his seminal paper. If the graph C-star algebras or Levitt path algebras are graded isomorphic or graded star isomorphic, then the matrices are shift equivalent. Okay, so I can see shift equivalence through, or I can extract shift equivalence through this lens of graph C-star algebras or Levitt path algebras, but the converse is not is for Levitt path algebras at least the converse is Hazarat's conjecture. This is still not known. So somehow it's a little surprising, you know, that the thing that's in the classical theory implying the isomorphism of the algebra, that's the thing that's not known. Normally it's the other way around in these sort of things. You start with something classical, then you can show that the algebras are isomorphic, and then you want to recover that thing. Turns out that the recovery process is easier than the encoding process through the algebras. So using non-commutative Röfling property, these are very deep analytic techniques in simple C-star algebra classification. There's a result of Bradley and Kishimoto saying that if A and B are so-called primitive, I'll explain what that means in a second, then A and B are shift equivalent if and only if the graph C star algebras are graded star isomorphic, not necessarily preserving the diagonal. Okay? So what does it mean to be primitive? It means that whenever you fix two vertices in your graph, and there is some length, starting from which there's a path of that length or more between these two vertices. Okay, so sometimes if you think of in terms of adjacency matrices, take your adjacency matrix, there's some iteration of the matrix such that all entries are strictly positive. That's an equivalent way of saying what I just did. So normally that, in general, that might fail because the matrix might not be primitive, it might not be irreducible. A matrix is irreducible if there's no invariant subspace for that matrix. Okay, that's equivalent also. Okay, so primitivity of A and B, really how is it used? It's used to say that the graph C star algebras are simple. So that fits within this Elliott classification program. Okay, fine. But there's no analog of this result for Levitt path algebras. So even for these primitive, or in the case of simplicity, of the graph C star algebras or Levitt path algebras, they're also simple in the primitive case. We don't know for Levitt path algebras the validity of this result, the analog of this result. Okay. Okay, so in what follows, I will say, and now comes in this concept of homotopy. I will say that these two graph C star algebras are homotopically equivalent if there are star homomorphisms rho and tau between these one and the other, and between the other and the one, yeah, such that composition in any order is graded homotopic to the identity. So through this homotopy, I have graded star homomorphism, and then at the very end I get the identity, which is a star isomorphism. But it's only at the end point of my homotopy that I need to be an isomorphism. Okay? So here's our main result. It captures shift equivalence in terms of graph algebras using homotopy. Let A and B be central matrices, then A is shift equivalent to B, if and only if the graph C star algebras are graded homotopically equivalent. Now, what is the thing here? Homotopy, in order to define homotopy, you need a topology, right? So for Levitt path algebras, it's not exactly clear how to define the same thing. But this has been done. I mean, there's something called algebraic homotopy, and this is work of Guillermo and Arnon. No, sorry, not Guillermo, Cortines and Arnon. And they define a sort of analog of homotopy, the purely algebraic setting, like the Levitt path algebras can be now over any field. They don't have to be over the complex numbers anymore. But the problem is that this notion of homotopy, this algebraic notion of homotopy, doesn't preserve K1, like the first K theory group. It preserves the zero K theory group, but not the first K theory group. So it's not a very operational thing. It's very complicated. It's not even a transitive relation in the purely algebraic situation. So it becomes more complicated if you want to define homotopy in the purely algebraic situation. Here, it's very natural because there's a topology. Okay. So one direction is actually covered by this Krieger's corollary because K theory is a homotopy invariant. Okay, so anything we say in terms of graded homotopy equivalence implies that the matrices are going to be shift equivalents. But the forward implication, which is normally the harder one, requires some new ideas. These ideas from theory of bicategories that I had alluded to. Okay, and they are absolutely necessary. I'll try to explain why. But first, I should probably mention that this is a question that Søren Eilers, my postdoc mentor, had posed to me when I was a postdoc at the University of Copenhagen, and eventually, this is characterizing shift equivalence for essential matrices in terms of these graph C stars. So eventually, we were able to do this after a few years. I don't know how many years had passed, but it's probably like 3 or 4 years that we've been thinking about this. Okay. So, bimodules. What are the contraptions used in the proof? So, if I take an adjacency matrix, I can turn them into finite dimensional bimodules over commutative finite dimensional rings, complex rings. So here are all commutative finite dimensional complex rings, right? It's C to the U, where you do just pointwise multiplication. Okay, so these are gonna be normed by modules. I'll tell you what the norm is in a second. I'm gonna dub it as XR. And it's just a vector space direct sum of C to the RUV, where RUV is the multiplicity of edges between U and V. Okay, and you can multiply an element in C to the U. I sometimes think about them as functions from U to C, right? That's what this finite dimensional commutative algebra is. Yeah, so I multiply F from the left by evaluating at the source, and multiply G from the right by evaluating at the range, and I keep psi evaluated at the edge. So these are the bimodule operations here. And it comes equipped with a norm. This one. Okay? So it turns out that balanced tensor products of these bimodules corresponds to matrix multiplication. And a path isomorphism induces a bimodule isomorphism. So it's a isometric bimodule map. But the point is, and this is a fine issue, it's not true the other way around. If you just have a bimodule isomorphism, it doesn't mean that you have a path isomorphism between the respective matrices R and S. And the reason is because of entanglement. This is why I call this quantization. What does entanglement mean for me? It means that an edge may not be mapped to an edge if I have an isomorphism of the modules, right? An edge could potentially be mapped to square sum to a linear combination of edges whose coefficients square sum up to 1, right? So this is the concept of a unitary, essentially, right? A unitary might not map a basic vector to a basic vector, but it always maps a basic vector to a linear combination of basic vectors whose coefficients square sum up to 1, right? So that's why there's some entanglement happening here, which makes things more interesting. So it's more free in some sense. Okay. All right, so let's make a definition. You know, I already talked about align shift equivalence. Let's take this align shift equivalence that we had defined previously and push it through this functor of taking this quantization that I did. So we say that XA and XB are align shift equivalent if there are matrices R and S with values in N, together with bimodule isomorphism. So same as before, only just between bimodules instead of matrices, or instead of edge sets, as we had before, and the same relations. This is a line shift equivalent. We don't know if it's equivalent to strong shift equivalence. As soon as we pass to the bimodule picture, we don't have the theorem anymore that this relation is equivalent to strong shift equivalence. We don't know that. However, a weakening of this relation, where you take, instead of equalities here in red, you take homotopy equivalence, characterizes shift equivalence. So I can reinterpret shift equivalence by having these aligned relations up to homotopy. This is an important observation. And the reason it's important is because of the following bicategorical interpretation. So the point is, you think, you know, bicategorically, morphisms map to morphisms, isomorphisms get mapped to isomorphisms, and homotopy equivalence should be mapped to homotopy equivalence. That's what happens in bicategory theory. Okay, or in category theory even. Yes? So this is something, if we can express this bicategorically, we win. Right? Because the result, after applying some functor that sends us to the appropriate category of C-star modules, would give us a homotopy equivalent, the homotopy equivalence that we want. Okay? So this is why this is this was extremely helpful to realize that this is actually a bicategorical notion here. So bicategory of modules, let me discuss this bicategory of modules. What is a one arrow, or the analog of a morphism in bicategory? It's a bimodule map between XA and XB. It doesn't have to be bijective. Okay? Some bimodule map. So if I have two such, so it's not just one okay, sorry, I should say, it's not just one bimodule map, sorry. Yes. If this phi of S does the following. XB and their XS. It's an intertwiner, right? It intertwines XA and XB through XS. That's this phi of S. So XS is considered as a one arrow together with a map that tells you how to move from here to here. That's called a one arrow. And you can compose one arrows, like so. XR tensor XS, and then there's this O dot product. What is this O dot product? It's exactly what you see here. This is this O dot product. Okay? Without the psi's. Forget about the psi and psi b, this is the O dot product. So here you already see the composition of one arrows appearing. Okay, what about two arrows? So these should be arrows between arrows, right? So I have a pair of two arrows with the same range, source in the same range, or the same domain and the same codomain. This is a bimodal isomorphism between XC and XD, which intertwines in this sense 5D and 5C. Okay? Turns out that this relation tells me that this psi A is a two arrow. This relation tells me that this psi B is a two arrow. Okay? Beautiful. So now, since we can interpret it in terms of bicategories, what is the functor here? The analog of a functor in the context of bicategories is called a homomorphism. Okay, because it respects compositions of one arrow and two arrows. Okay, so this forms a two category, a weak two category, or bicategory. What's the difference between a category and a bicategory? In category theory, you ask for diagrams to commute on the nose, equality. In a bicategory, you can do this merely up to isomorphism, which you keep track of. And this is this two arrow that comes into play. So everything commutes up to two arrows. Okay, that's the point. So there is a homomorphism of bicategories, sending finite dimensional modules to C star algebras graded over the integers. It sends XA to the right C star algebra. It sends XA, the one arrow, XAN with this morphism, with this phi to a graded star isomorphism. So if you plug in the identity here, you just get a graded star isomorphism. This is important. And homotopy between one arrows induces a graded homotopy between their associated graded star isomorphism, star homomorphism. So what is this? This here is just a homotopy of between one arrows. Yeah, just like here. This notion, sorry, without the equality, but rather with equality replaced with homotopy equivalence here, yes, you do get a homotopy between one arrows. So now you say it's shift equivalent, therefore XA and XB are homotopy shift equivalent, which is just a homotopy between one arrows, and that induces a graded homotopy equivalence between the respective C star. Okay. So I think with that, I have a proof here, but I'll skip it. I think with that, I will conclude. Thank you.
Questions from the audience?
Okay, so you have two decision problems, right? One is, as far as I have, is known how to solve,
Yes.
and one is difficult. And for the one that is known how to solve, what is it known as the complexity?
Oh, no. No, they didn't go through that, no. So they have a paper where they bound the necessary given two matrices. In terms of their size, they can tell what is the maximum lag that you would need to verify shift equivalence. Yes? And as soon as you can bound the lag, even if it's in terms of the matrices, then it's decidable. Then you can run the algorithm because you just go until you reach that lag. And the lag is the problem. For strong shift equivalence, you cannot bound the lag. It's not known how to bound the lag that you need to go through. It could be potentially arbitrarily long, even independent of the size of the matrix.
So this is not known to be recursive function of the computer.
Oh, I don't think so, no. Yes.
It's the bicategory, there's a bigroupoid. Is it somehow related to this bicategory?
So what is a bigroupoid?
It's like you have two arrows, you can compose horizontally and vertically.
Potentially, I don't know.
Okay.
Yeah, I don't know. But yeah, maybe I would say this. If you just try to do this categorically, yeah, I was trying to make this pitch, right? That the bicategory is absolutely necessary. If you if you force category theory here, so diagrams commute up to equality, people have tried to do that. And that has led to significant mistakes in several papers. Okay? And we, in one of our papers, we actually show that the categorical approach cannot work. Very, very difficult result. Why? Because it relies on a reduction to this counterexample of Kim and Roush from the annals. Yes? So this is the solution. If you keep track of the isomorphisms of the identification that you're making along the process, this is what you do in a bi-category, and you don't do in a category, then you win.
Okay, no more questions. Thank the speaker again. We'll have a dinner tonight at 6:30 at the hostel. If you want to come, feel free to email me and or just show up. You have made a reservation for 12. Thank you for coming.
Thank you.